All right. Morning, everyone. Today we're going to finish off the chapter. It might be a bit short today, but might have a few video examples at the very end. So stick around for that. Let's continue from where we were yesterday. I was going to do an example on a harmonic wave. And this primary example was to show us how to find the energy, or at the very end. Let's get to it. I need to do one. Okay, so a harmonic wave of wavelength 25 centimeters in amplitude 1.2 centimeters moves along a 15-meter long segment of a 60-meter long string that has a mass of 320 grams and a tension of 12 newtons. What we want to find is what is the speed and angular frequency of the wave, and what is the average total energy of the wave. Okay, so let's start out with that first part. It's just like that. What is the speed and angular frequency of the wave? Okay, so there was a wave on a string where we know what the equation to find the velocity of a wave on a string is. That will be V equals, see if I can remember it, it's square roots of the tension over the linear density. This is a mu, Greek letter mu. And I'll say where mu is, that's the mass, that's the total mass of the string over the total length of the string. So we're just seeing how dense each individual little section of this string is. So let's take that density, just take it right back into that equation. And we could rewrite that velocity formula as F tension over, there'll be mass and there'll be a length on the numerator like this. Okay. Then from here on, it's pretty straightforward question or problem. We have the tension's already given to us, 12 newtons. We have the total length of the string, 60 meters. And we have the total mass of the string. And I'm making sure to have this all in SI units. I'm going to convert the mass to kilograms. 0.32 kilograms. All of that is under a square root equals a velocity of the string. All right, so that shows that. Let's see. All right. Hey, morning. We're going over a small example from the start of last week's class we're asked to find the velocity of this wave on a string. So I'm using the velocity for a string formula. And this is a string. It uses a linear mass density. So that's this mu right here. And after some sort of rearranging, I've arrived at finding the velocity of the wave. That's the first part of this example. And we get 47 meters per second. Okay. What is the next part? What is the average total energy of the wave? This is one of from the last set of notes that I did. It was just sort of the extra bit I tacked on near the bottom. We would just use the equation for energy. I don't know if okay, yeah. We're given the amplitude. All right, so let's go ahead and solve for the energy in this case. So actually I want to go like this. So let's write down the formula first. It's the change in energy, and this is of the entire string, and it's just an average. So average, that was 1/2. Let's see. It's the linear density times the frequency squared, amplitude squared, and whatever segment I'm looking at. And in particular, I'm just going to be using the mass density that I've just solved for up here and putting it into the equation. Okay. Mass over length, omega squared, a squared. Okay. Nothing too demanding for this problem, since most of this stuff is already given. Now the mass density is the entire mass and the entire length. Let me do, so the entire mass over the entire length, 60 meters. And we want the, let's see if I could, there we go. We need omega. Oh, that's what, yeah. So I could do this, omega squared. We still need to solve for omega, so that's what is not currently given. Let me fill in the rest of this. And I'm going to leave some space so I could put the omega in after I solve for it. Okay, that amplitude is given as 1.2 centimeters, wanting everything in SI units. So 0.0. Nope. There we go. 2 meters squared. And this is the specific sort of segment that I'm looking at, which is only 15 meters long. Okay, so we are given everything for this except for the omega, the angular frequency. We need to find that first. So let me actually, what I'm going to do is solve for that up in the top. Go like this. Or some of the, this was also one of the really long, I could have made it a long chain of formulas, like a equal sign, omega equals this, it also equals this, and this, and this. What I'm specifically using for this case is omega is 2 pi times the frequency, where the frequency, or let's go, I guess I'll say where V equals frequency times the wavelength. And we just solved for the velocity. So we have that now. And we have the wavelength. It's given above. Or sorry, we have the, no, yeah, we are. It's not this, it's this right here. So we have the velocity and a wavelength. So that's why we're wanting this. I'm going to solve for the frequency. And take that, put it right back into there. 2 pi velocity over wavelength. 2 pi, the value we just found, 47 meters per second, over 25 centimeters. We want this in SI units. And let's see, 0.25 meters. Okay. So in this case, the meters, the unit of meters cancels out. So we have a total result. Let me space this out a bit so it looks better. So omega equals, the angular frequency equals 190 versus seconds. Okay. Now we're going to take this results and it will go right into the thing that we needed it for. And it is squared. Let me look at one thing real quick. Okay, I think we're good on, yeah. Just checking the units. Okay, I think we're fine. In the end, we have a energy of average energy of this specific segment. Average energy of this specific segment is 8.2 joules. This can be useful for if you're looking at, say, you want to see what kind of energy an actual physical water wave might be delivering to a wall, a construction that you need to see how much energy is this thing delivering in this specific range. Can my building or pier or whatever withstand this amount of energy being delivered to its structure? This energy, it has to go somewhere, and if it's brought to this border or something, it has to then be dissipated somehow. All right, so that was the example for this section. Let me move on to something just slightly different. This chapter goes over a couple different types of waves, like light waves or electromagnetic waves. I'm going to skip over that just a little bit. I might add on, I think, yeah, I'm going to skip over some of that, but I will go over the Doppler effect right now. So we have, let's go at this. We do have the Doppler effect. The Doppler effect is something we experience every day without really noticing. If you've ever been at sort of a railroad crossing, you hear a train coming, the train will approach and the horn will be going off to warn people that it's coming. And you'll sort of hear it at a higher pitch when it's coming towards you. And then right when it passes you, the pitch changes and it gets sort of lower as it moves away from you. The pitch of the horn. This happens with a train horn. It happens at you can notice it with cars that pass by. You can notice it with pretty much anything that is moving and emitting a sound. It's pretty apparent with sound waves. The Doppler effect also works with light waves, and I'll sort of explain that after I go over the concept. Pretty much any type of wave. So we have, if a moving object emits a wave, this resulting wave will experience a change in frequency. This is a result of the Doppler effect. So say we have a car. I think a lot of my examples involve a car horn coming up. So let's say we have a car horn going off and the car is parked. It's stationary. Let's go like this. This is a stationary source for this wave. So imagine this is a three-dimensional picture. I can draw like all of these spheres inside of each other. And also there would be the ground involved. But imagine maybe this is a top view. Yeah, think of this as a top view of a car with its horn going off. It is a stationary source. So as the car horn is going off, it's emitting this sound wave that's being propelled in every direction in a large circle. And the waves themselves are moving outward. The waves themselves, let's go like this. Each of these waves, you see they're equally spaced apart. That's showing the frequency. Each of them are moving at the same exact speed outward in every direction. You can maybe see why this, or how this could be difficult to draw. So every single one of these waves is moving outward, the same speed. Each of these, all of these waves are moving at a speed of v. So let me try to make this clear for later. People looking at the notes later. We have speed of the wave, v. And we have a stationary source. So the dot in the middle, that's just staying still. Now, what if we take that dot or we take that car and we start moving and having the horn go off at the same time? So it's still emitting these sound waves, but the car itself is moving with the sound waves. So maybe in one specific direction. Let's go and show this one. So let's say the car is moving to the right. This will be the picture in this case. So the car is moving to the right. So the sound waves it's emitting will be compressed on one side and expanded on the other. Since this car is moving, how do I want to draw this arrow? We'll put it, we'll put it in, we'll go like this. So since the source is moving, I'm going to call that U of S. Now, I know it's not, we've typically been using V for the speed and the velocity. Since there's going to be a lot of different speeds I need to keep track of, I'm using this new term U for this object that is moving. But keep in mind that all of these waves that it's emitting are still moving outward at that same, they're all still moving outward at the speed v. So let me clarify up here, this is a moving source now. So what if we had an observer looking at the this scenario? If we had an observer, I'm going to make it just a sort of like a floating eyeball looking off to the side like that. So they are looking towards, so that's an eyeball and it's sort of sitting right here. and it's looking that way, and it's seeing that this car horn is going off, and the waves will approach and pass by this observer right here. Since they're all moving outward, and they're all going to be at the same spacing that they left the car itself. So nothing really happens to the frequency for the observer looking at this. And the same thing, I could put the observer on this side of the, the car, same thing, it sounds the same. So instead of an eyeball, I could make this like an ear. But I don't want to draw an ear on the spot right now. So what if we look at this moving source? If we have an observer over here, and this car is approaching and emitting the horn, so it's honking the horn while going towards this observer, the sound waves are going to pass the observer, but you see they're spaced out much smaller right here on this side. So that means over the same span of time, you're going to hear more beats, hear more waves. And the more you hear in a second, that means it's more frequent, so it's a higher frequency. Okay, if you have an observer over here and the car is moving away from you, the waves themselves are more spaced out. You're hearing the beats less frequently, so it's a lower frequency. And this is the primary, factor in hearing things, shift upward or downward in their tone. I use the word tone. I'm really just meaning the frequency of this sound. It's changing as the object itself might be moving. So let me, all that's good. Let me, I'm going to write out the variables I'm going to use before I start just throwing a lot of new variables on the screen. So we have V, we already know that. That's the speed of the wave. We have F of S, so that's the frequency of the source. We have U of S, that's the velocity of the source or speed of the source. And we have F of R, which is frequency of the receiver. So this observer over here. You go like this. And U of R, speed of the receiver. Okay. Now that we have this sort of all laid out, before I start throwing equations up on the board, let me sort of say what would happen for a stationary receiver. So that's like the picture I have above. The Ooh. The picture I have above, the observer is staying still. The observer right here is just motionless and staying still. So for a stationary receiver, we have the equation. It's the same equation that we have found before for the velocity of a wave. I'm just going to add the new variables in. So the frequency of the receiver times the wave length is equal to the velocity of the wave. I could also find the this new wavelength. We go like this. Plus or minus. So what's the wavelength going to be? I want to explain before I do it. So the wavelength for this stationary case, we know the wavelength is just this right here. Just one of those. It could be this little bits, or it could be a section right here, but it's all the same everywhere on this stationary example. Or I don't even have to go from the lines. I could go middle of this line to middle of this line. And that's one wavelength. It'll always be that way. But since we have this moving source, the wavelengths are all different everywhere around this thing. So this wavelength over here is much bigger. I couldn't make it more dramatic and save the space on the page, but it's much larger. This one right here, it's much larger than it normally was over here. And by the same logic, this over here on the right, much smaller wavelength. So the wavelength changes depending on the direction and the speed of the source. The speed of the source right here. So for this wavelength, the stationary receiver can sort of figure out how to find this wavelength by looking at the speed of the wave, v, and we're going to do a plus or minus. The plus or minus is just dependent on which side of the wave you are on. So I have this observer right here. Observer on this side will have a different experience from an observer on this side over here. So I guess I could also put receiver. There we go. So plus or minus, if the wave, this is where we just have to determine for ourselves if we are adding or subtracting. Is this wavelength getting bigger or is the wavelength getting smaller? We need to physically picture this example in our minds. Let me stop doing that button. Okay, so is the wavelength getting bigger or smaller? And then we pick a plus or a minus. We're here. Velocity of the wave, plus or minus the velocity of the source. And this is the period of the source, but I don't like having that. Introducing a new variable, so I'm just going to leave it as v plus or minus the velocity of the source over the frequency of the source. All right. And using this, I've pretty much found the wavelength. I could put it right back into this equation and solve for the frequency heard by the receiver. That is the speed of the wave over the speed of wave plus or minus the speed of the source in the original frequency of the source. So if we have a given value, we know it should be, or we know what it is producing, we know a original frequency produced by the source. Now this is for something that is moving towards a receiver. What if the receiver or this observer is moving towards the source? So now I have to picture, take one of these eyeballs. Now, picture that I am on a train, or I myself am in a car and I'm moving towards a parked car with that parked car's horn going off. So this right here is me, and I am moving towards it at a steady speed. What sort of experience am I going to have hearing the shift of the tone? Well, let's make a general form that we can use. We can use it like a real general form. And that way we can determine actual values from this. Let me go, because it intuitively, I think it's going to be similar to this case, but I don't know if it's going to be exactly the same. So let's make this general form. And we'll say that for this receiver, maybe the receiver itself is moving. Well, then we can, do this. The receiver is the velocity of the wave plus or minus the velocity of this receiver, now that it's moving, over the wavelength. And this is, you imagine the actual wavelength. The the receiver is the only thing that's changing in this case. Let's go, yeah. Ultimately, we get a final form that looks like this. And this is a general form that we can use for any Doppler effect problem. Let me shrink all of this and make it look better. If we have a moving source or a moving receiver, we can determine what the frequencies were or should be. We could also determine how fast something might be moving if we already know some frequencies. Let's do an example to maybe show this in action. Yeah. This will be a real quick example. Okay. So this is exactly the scenario I pitched for that for my drawings. We have a car horn that's going off, and we know what it should be. The car horn is emitting a frequency of 400 hertz. And in this first case, we're having the car move with a speed of 34 meters per second towards a stationary receiver. Stationary receiver. For this first part, we want to find the wavelength, and for part B, we want the frequency. Okay, so those two things should be pretty simple. Wavelength, that will be V minus S over frequency. And that back out. Okay, so this is a stationary receiver, and let's see. So it'll be like that moving source picture I had before. It's moving towards, it says moving towards a stationary receiver. So the wavelengths I'm expecting should get smaller as it approaches. So that's why I am picking a minus sign right here. Sort of justifying that. Then we have this. This is just a math problem now. 34 meters per second over the frequency of what it was emitting. 400 hertz. We get a wavelength of 0.76 meters. Part B, we want to find the frequency of the frequency received. Right, and that's, where am I getting this 343? It is right here. That is the speed of sound in air. It doesn't give us like temperature of the air, so we're just going to assume it's always going to be this constant speed. So that is V. Let's do this. Let's do the general form for this receiver. So what is the receiver going to pick up? V plus or minus UR over V plus or minus US FS. Okay, so car moving towards a receiver. Car moving towards a receiver. Well, the receiver is stationary, so this U of R term right here will be 0. So I don't even have to worry about that part. then it will be just this that remains. V over V plus or minus U of S. So let's write that. V over V plus or minus U of S. F of S. It is a frequency that is, as the car is approaching, the wavelengths will get smaller. It will become more frequent because the waves are sort of being compacted together. I will the receiver will see them sort of bunched up with a higher frequency. So how can we make this value bigger? So will we need to have a bigger or a smaller denominator if we wanted the whole thing to be larger? So we would need a smaller denominator. So that's why I'm going to go V over V minus U of S. All right. And from here on, it's just inserting the values that we have. The speed of sound in air, 343 meters per second minus however fast this car was moving, 34 meters per second. And the frequency of the horn that it's emitting. We're going to say just about 450 hertz. So say we've measured it before the car started moving. Now that the car is going out and it's doing a test drive, it's driving towards you. If you have a little meter that picks up the frequency, you see the frequency has grown. It's no longer 400, it's 450. So this will result in a sort of higher pitched sound from this horn. All right, now here's the interesting part of the problem. Part C says that now consider a receiver that is moving at 34 meters per second towards a stationary car. Stationary car that is honking the horn. Was the wavelength and frequency of the waves detected? For me, I would also, or I'm one to think it's just going to be the same because it's the same speed. The receiver is now moving at 34 meters per second, whereas for this first two parts, the source was moving at 34 meters per second. This is where we actually need to do the calculation to show that we need to do the calculation to sort of prove this. Just to see. So let's try it. So for the wavelength is, let's do the general form. U S over F of S. Okay, well, in this case, the car is not moving anymore, right? So this is 0. Okay, interesting. So that means we only have 343 meters per second over 400 hertz. Now I'll give us a wavelength of, and I'll say about, because I'm doing some rounding, wavelength of about 0.86 meters. Interesting. It's not the same as above. They're not equal. Even though the receiver is moving towards the car at the exact same speed. What's going on here? Let's continue. Was the frequency of, or the frequency detected by the receiver. Frequency detected. We'll do the general form. Velocity of the wave plus or minus velocity of the receiver over velocity of the wave plus or minus velocity of the source. Frequency of the source. Okay, so now in this case, do this. So in this case, the car or the source is stationary. So this goes to 0 now. That'll give us a different result in how this fraction is ordered. Times Fs. Okay, so this does not look like this. Merely just because the receiver is moving in this case. I'll say since the receiver, since it's moving towards the let's see, since it is moving towards the car honking the horn, we will say it is a positive. Let's see. That's because we want the frequency to get bigger. Remember let me do a little drawing. It's hard to do this without a drawing. The waves themselves are getting more compact, so we're experiencing more of them. So we want a larger frequency. So how would we make this fraction larger? We would need a larger numerator on this example. So we'd need this to be larger. That's why I'm going to be adding the top in this case. And that just results in this form. I'm going to sort of simplify so it will look like this. All right, now we have all of the factors of this problem. Let's take them and continue. The speed of the receiver is moving at 34. The speed of sound waves in air, 343. That. The frequency of the source was 400 hertz. We get a frequency now received that is just about, so I'm just keeping everything nice and approximate. This is just about 440 hertz. So this is not the same as that. So it does depend on whether or not the source or the receiver is moving. And it's because of the Doppler effect, it's because of this process I just did right now, that you can learn a whole lot about the situation. You can say how fast, as long as you know the appropriate pieces, you can know um, how fast the receiver is moving. You could also figure out how fast the source itself is moving. Say you were sort of blindfolded and you were given this problem, you would have a way to figure out, oh, the receiver, or sorry, this car horn, it's not because the car is approaching me, it's because I am approaching the car horn. So that's a way to determine, using the Doppler effect, what exactly is going on. Now, let me do a little bit of cleaning up like that. Okay. I have a, let's see, what time is it? I have a little sort of simulation example that is pretty much all I needed to explain the Doppler effect. Well, I still had to, draw some pictures. Let me take this, bring it over here. All right. So we have the Doppler effect, little simulation. We have the source as this sort of dot on the left, and we have the receiver or observer as this green line on the right. I'm going to, let's see, so it's stationary. Okay, so this, for a lot of this time I've been saying a car horn. It doesn't have to be a sound wave. It can be a light wave. Actually, this process that I've been showing can also be done with light waves. Light waves can sort of, their wavelengths can be stretched or shrunken. This is actually how, in astronomy and astrophysics, that's how we're able to say, oh, this galaxy, millions of light years away, we can actually tell that this sort of galaxy that we're seeing is moving away from us, or this one is moving towards us at this certain speed. It's because we know what some specific wavelengths should be of this galaxy, and we notice that the wavelength of this light that's reaching us, it's not what it should be. It should be this. So the source was emitting this, but we are receiving this wavelength. So that means this velocity of this galaxy is, approaching us or moving away from us. Yeah, so that's called blue shift or red shift. As something is, for light, as something is approaching you, the wavelengths get smaller or shorter. So the color itself is shifted to look more blue. Or if something is moving away from you in light waves, the wavelengths will stretch out a bit and appear more red if you're looking at it with a telescope. All right, so for this example, we have a stationary source emitting a constant periodic wave. All of the waves move outward at the same speed, and they dissipate sort of on the edge. But we have this stationary source stationary receiver. In this case, the car horn example, the car horn sounds as it should be. Now, let me reset, pause. Let me move the observer. It's right here. That'll be more helpful. So the observer hearing something as it should be. Now, let me say that the source itself is moving towards the observer. You see, as the waves are emitted, they sort of bunch up near the front and spread out on the backside. Make it just a bit less dramatic. There we go. And if you can see this sort of neat simulation, it does the frequency experienced by the observer right here. As the source passes by, the frequency received is different. As this source speeds up, let's say it's exactly 1. In this case, the source is moving at the same exact speed of this sound wave, or this wave it's emitting. In this case, this is like a fighter jet can move at such a high amount of speed that if it was to emit any sound, it would be moving as fast as the sound it's, producing. But like you might know for a fighter jet, if it moves even faster than sound, it will develop a sonic boom. This is where it will break this sound barrier. Imagine this line right here as the sound barrier. All of its sound can't move faster than this, but the jet itself can. So let's see what that would look like. It would look like something like this. See, the blue dot is moving faster than the sound it's producing. And this is why those sonic booms from the jets fly above, they're so violent, because all of the waves, imagine imagine my mouse right here as us on the ground. So if we were right here on the ground, look at all of those waves are sort of colliding and approaching us. They'll cross our path all at the same time. Yeah, so there's that. What about if the source is moving away from the observer? Again, sort of experiencing this spread out effect. I think the last thing is, this one is not as fun to look at, but if I'm moving the observer, it's experiencing the waves, and the waves are moving out at the, the same frequency, but the observer is experiencing them differently. Reset. There we go. So as it's moving towards on one side, it was a higher frequency. As it passes on the other side, it moves to a lower frequency. Set one more time. So high frequency and low frequency. All right. I think I didn't find a good video that I liked. Yeah, I didn't find a good video I liked. In class, if we were doing this in class, we have like this a tennis ball that's attached to a string, and inside of the tennis ball there's this little speaker that makes a high-pitched sound, and the high-pitched sound is being produced at a constant sort of volume and a constant frequency. So we hear it as a constant high-pitched tone. And what I would do is take this tennis ball and I could swing it over my head, and for part of this path, it is moving towards you guys in the audience. So for one side, the sound waves are being bunched up, and as the ball passes by the other side, the sound waves are being spread out. So you would hear this sort of changing, fluctuating pitch of this thing, even though I could show you that I could stop spinning the tennis ball and the pitch would be still constant. It's just the Doppler effect in action. All right, I think that's it for all I want to cover in this chapter. Tomorrow I will, if anyone has questions, we can go over them. But if not, I'm going to start the next chapter on superposition and standing waves. But we only have one more class lecture left tomorrow. So as always, if you guys have any questions, just let me know. If not, I hope you have a good rest of your day. I'll see you later then.